Good day, everyone. We are from the Department of Statistics of the CUHK. Welcome to this engaging presentation on the fascinating topic of derivative and shape of graphs, Part 2. Throughout this presentation, we will delve deeper into how the higher-order derivatives, concavity, and inflection points help us understand the shape and behavior of different types of functions and graphs. These concepts build on what we learned in Part 1 and will provide powerful new tools for graph analysis. Let me briefly walk through the main points we'll cover today. First, I'll define higher-order derivatives and demonstrate how to compute them through some illustrative examples. Next, we'll explore the idea of concavity and I'll show you how to use the second derivative to test for concavity. After that, we'll discuss inflection points and I'll explain how to locate them using the second derivative. Finally, I'll summarize the key takeaways and conclude the presentation. To kick things off, let's recap what we learned about derivatives in Part 1. Previously, we saw how the first derivative can tell us where a function is increasing or decreasing. In this chapter, we'll expand on that foundation by introducing the concept of higher-order derivatives. We will also see how the second derivative provides information about the shape of a graph by describing whether the graph of a function curves upward or curves downward. Let's begin with higher-order derivatives. Specifically, a higher-order derivative is simply the result of taking the derivative multiple times. For instance, if we start with the function y equals f of x and take the first derivative, we get y prime equals f prime of x. If we differentiate again, we arrive at the second derivative. Y double prime equals f double prime of x. We can continue taking derivatives to reach the third, fourth, and so on. Let's look at the precise notation and rules for calculating higher-order derivatives. There are a couple common notations we can use to denote higher-order derivatives. One way is to use Leibniz's notation, which uses fractions with powers of d over dx. For example, the second derivative can be written as d squared y over dx squared, and the nth derivative can be written as d to the n y over dx to the n. Another way is to use Lagrange's notation, which uses primes or dots above the function name. For example, the second derivative can be written as f double prime of x or f dot dot of x, and the nth derivative can be written as f to the nth power with parentheses around it or f with n dots above it. To actually find higher-order derivatives, we simply apply the derivative rules we already know repeatedly. Let's try some examples so you can see it in action. The notion of the nth-order derivative is introduced inductively by sequential calculation of n derivatives starting from the first-order derivative. Transition to the next higher-order derivative is performed using the recurrence formula y to the nth prime equals y to the n minus 1 order derivative prime. Sometimes, we can also find a general formula for higher-order derivatives without computing intermediate derivatives. It is important to note that in some cases, we can derive a general formula for the derivative of an arbitrary nth order without computing intermediate derivatives. Also note that linear relationships can be used for finding higher-order derivatives. U plus v to the nth prime equals u to the nth prime plus v to the nth prime, and cu to the nth prime equals c times u to the n, th prime, where c is a constant. Be careful with the non-prime notation for derivatives. For instance, f with 2 in parentheses at x equals f double prime at x, while f squared at x equals f at x squared. The presence of parenthesis in the exponent denotes differentiation, while the absence of parenthesis denotes exponentiation. Let's see some examples of how to find higher-order derivatives. Please refer to the slides on screen for more details. For our first example, we'll find the third derivative of f of x equals 2 pi squared over 6 minus x. To find this derivative, we can simplify the function first by writing it as 2 pi squared times 6 minus x to the power of negative 1. Then, we can use the quotient rule and the power rule to find each successive derivative. The first derivative is 2 pi squared over 6 minus x squared. The second derivative is 4 pi squared over 6 minus x cubed. The third derivative is 12 pi squared over 6 minus x to the fourth power. In this second example, we need to find y double prime for x squared plus y to the fourth power equals 10. To find this derivative, we can use implicit differentiation twice. First, we differentiate both sides with respect to x and get 2x plus 4y cubed times y prime equals 0. Then, we solve for y prime and get y prime equals negative x over 2y cubed. Second, we differentiate both sides again with respect to x by the quotient rule. Then, by simplification and substitution, we get y double prime equals negative 2y to the power of 4 plus 3x squared over 4y to the power of 7. As you can see, we can leverage the derivative rules we already know to systematically calculate higher-order derivatives. Now let's see if we can find a general formula. For this third example, we will derive a general formula for nth derivative of y equals natural logarithm of ax plus b. To find this formula, we can use the chain rule repeatedly and observe a pattern. The first derivative is a over ax plus b by the chain rule. The second derivative is negative a squared over ax plus b squared by applying the power rule. The third derivative is positive 2 factorial times a cubed over ax plus b cubed by applying the chain rule and power rule again. In general, we can see that the nth derivative is negative 1 to the power of n minus 1 times n minus 1 factorial times a to the power of n over ax plus b to the power of n. This allows us to bypass computing each lower order derivative separately. Let's look at one more applied example. Suppose a robotic arm moves according to the displacement s in meters equation. S equals 1/6 t to the 4th power minus 7/6 t cubed minus 2t squared plus 3, where t is time in seconds, for t greater than 0. How can we determine when its acceleration will equal 0? To find this, we can use the fact that the acceleration is the second derivative of the displacement. Let v represent the velocity, which is the first derivative, and a represent the acceleration. The velocity is 2/3 t cubed minus 7/2 t squared minus 4t by applying the power rule. The acceleration is 2t squared minus 7t minus 4 by applying the power rule again. Now we have to solve when equals 0. We can factor the quadratic equation and get 0 equals 2t plus 1 times t minus 4. The solution is t equals negative 1/2 or t equals 4. We reject t equals negative 1/2 since t has to be positive. Thus, at 4 seconds, the acceleration of the robotic arm is equal to 0. That concludes our overview of higher-order derivatives. Let me know if you have any other questions. Next, we'll transit into exploring the very useful concept of concavity and how to test for it using the second derivative. Moving forward in our journey, we arrive at the idea of concavity. Concavity characterizes the shape of a graph, whether it opens upward or downward. Referring to the graph on screen, a function is concave up if it opens up and the function is concave down if it opens down. Notice as well that concavity has nothing to do with increasing or decreasing. A function can be concave up or down while increasing or decreasing. Let's formalize the definition before seeing how to test for concavity. More precisely, concavity is determined by the function's tangents. Recall a tangent line touches the graph at one point and matches the slope there. If all tangents on an interval stay below the graph, the function is concave up there. If the tangents stay above, it's concave down. Visuals can really help solidify this concept, so let's refer to the graphs on screen. Luckily, we can use the second derivative to easily check concavity. The second derivative tells us how fast the slope of the function is changing. Here are the key theorems. Theorem 3.1 states that if the second derivative of a function is greater than 0 for all x in some interval I, then the function is concave up on I. The proof of this theorem involves using the mean value theorem and the fact that if the second derivative is positive, then the first derivative is strictly increasing. This means that the tangent line to the function at any point in the interval will always be below the graph of the function, indicating that it is concave up. Similarly, Theorem 3.2 states that if the second derivative of a function is less than 0 for all x in some interval I, then the function is concave down on I. The proof of this theorem also involves using the mean value theorem and the fact that if the second derivative is negative, then the first derivative is strictly decreasing. This means that the tangent line to the function at any point in the interval will always be above the graph of the function, indicating that it is concave down. Let's see how this concavity test works on a sample graph. Remember, concavity and increasing-decreasing are independent. In summary, to check concavity at a point, if f double prime of p greater than 0, the function is concave up at p. If f double prime of p less than 0, the function is concave down at p. However, if the second derivative of a function is equal to 0 or does not exist at x equals p, then we learn nothing new about the behavior of the function at x equals p. Let's solidify this with an example testing the concavity of an exponential distribution. Suppose we have a random variable x that follows the exponential distribution with parameter lambda greater than 0. Then, the cumulative density function of x is given by f of x equals the probability that x is less than or equal to x, which equals 1 minus e to the negative lambda times x, where x is greater than or equal to 0. We want to show that f of x is concave down for all x. To do this, we can find its second derivative and check its sign. The first derivative of f of x is lambda times e to the negative lambda times x. The second derivative of f of x is negative lambda squared times e to the negative lambda times x, which is less than 0 for all x. Therefore, f of x is concave down for all x greater than or equal to 0. That concludes the key ideas around using the second derivative to analyze concavity. Now we'll look at how to locate inflection points on graphs where the concavity flips. Now that we know about concavity, we can introduce the inflection point. With the decreasing information from the previous chapter, we can get a pretty good idea of what a graph should look like. An inflection point is a point on the graph where the concavity changes. In other words, it is a point where the graph changes from concave up to concave down or vice versa. Please refer to the definition on screen for more details. Definition: given a function f of x, then a point x equals c is an inflection point of f of x if f of x is continuous at x equals c and the concavity of f of x changes at x equals c. To find inflection points, we can again leverage the second derivative. Specifically, if the second derivative changes sign at a point, that point must be an inflection point where the concavity switches direction. Please refer to the graph on screen for more details. Let's conclude by a full example of locating inflection points on the standard normal distribution graph. For a standard normal random variable x, its probability density function is given by f of x equals 1 over the square root of 2 pi times e to the power of negative x squared over 2, for all x in R. To find the inflection points of f of x, we can find its second derivative and check its sign. The first derivative of f of x is negative x over the square root of 2 pi times e to the power of negative x squared over 2, which equals negative x times f of x. The second derivative of f of x is negative f of x plus negative x times f prime of x. Set f double prime of x equals 0, we have x equals negative 1 or 1. We also know that f double prime of x is greater than 0 for x less than negative 1 or x greater than 1, and f double prime of x is less than 0 for negative 1 less than x less than 1. Therefore, the inflection points are negative 1, 1 over the square root of 2 pi times e to the power of negative 1/2 and 1 over the square root of 2 pi times e to the power of negative 1/2. As we wrap up, let's recap what we've learned today. We explored higher-order derivatives and saw techniques for computing them. We discussed concavity and how the second derivative reveals it through the concavity test, and we identified inflection points where concavity flips using the second derivative. These concepts provide deeper insight into the behavior and shape of functions and their graphs. I hope you found this presentation on derivatives informative and useful. Thank you all for your time and attention today. Please reach out if you have any remaining questions.